Yeah, my name is David Rowe. I'm from Adelaide, South Australia, and I'd like to talk about an open source speech codec I've been working on for the last few years called Codec 2. It's a low bitrate speech codec, probably lower bit rates than most of you are accustomed to, in the range of 2000 bits per second and below. Currently got a 2400 bits per second mode and a 1400 bits per second mode under development. The main applications are digital speech for HF and VHF radio. The idea of Codec 2 is to fill a gap in the open source landscape for speech codecs beneath 5000 bits per second. There's been a lot of good work done by projects like Speaks and Opus and the Vorbis stuff above 5000 bits per second, but there's a bit of a gap beneath 5000 bits per second, in particular for the digital radio applications. And you can get samples and source from the URL rotor.com/codec2. This is not going to be much of a DSP talk. These are all the topics I won't be talking about. But if you would like to talk about them, I'm happy to do that later, and I've got plenty of other information on them. Instead, I've tried to pitch this talk at you guys. It's stuff I can explain, and I want all of you to take away 3 or 4 things about speech coding and the related applications and open source implications from this talk. Instead, I've got a bunch of random tangential topics that do map to the codec, as you'll see towards the end. I'd like to talk about patents and codecs, voice over IP and digital radio, ham radio and the proto-geeks that we're all descended from over 100 years ago. I've got a little demo of the speech codec and talk a little bit about how room acoustics affects that. Speech coding and weapons of mass destruction, how they were recently related to me together, and I'd like to say a little bit about why voice is not like data over channels and why you shouldn't treat it the same way. And then I've got a relatively non-DSP graphical description of how Codec 2 works. What can you do with Codec 2 at 1400 bits per second? A standard telephone call, the sort of thing that goes over ISDN or through a regular telephone exchange, uses 64 kilobits per second. You can send 45 of those phone calls using Codec 2 down the same channel. So a compression ratio of 45:1. It's only 175 bytes a second. You can put a 30-second voicemail in only 5 kilobytes and an audio book or a 30-minute podcast in only 300 kilobytes. So it's a very tight compression ratio. It's not so useful for VoIP. The main reason is that when you transmit a packet, a voice over IP packet over the internet, there's a bunch of overhead involved. You have to take the payload data, which is only 7 bytes every 40 milliseconds in this case, bundle it up in an IP, UDP, RTP headers, which are 40 bytes. So what you end up doing is having about 85% of the bandwidth you're using being consumed by overhead. And headers if you're only coding at 1400 bits per second. So once you get much below around say 8000 bits per second, you start to get diminishing returns for VoIP, for speech compression. One approach to get around this is to concatenate speech packets, so you could buffer up 80 milliseconds or 120 milliseconds before sending it, but unfortunately latency starts to pick up, and when you add the network delays, there's not much profit in that. What you can do is trunking. If you have say 45 phone calls all going to the same destination over the internet, you can bundle them up in one IP packet and then get some of the benefits of these sort of compression ratios. But in general, this sort of codec is not that useful for voice over IP or internet applications. The main application is voice over digital radio. The issue here is that RF spectrum is really limited. There's only so many megahertz available that we can use, so there's a lot of advantage to having a codec that can send voice over very narrow bandwidth and very low power levels. The other problem with digital radio channels is when you stick a bit in one side, you're not guaranteed to get the same bit out the other side. There's noise, there's a lot of bit errors, and that tends to corrupt the signal. So it's pretty different to the sort of Ethernet type or IP packet channels that we're used to using. Now, people to send voice over digital radio channels, a lot of people are still using traditional analog speech systems such as frequency modulation, single sideband operation, such as FM or SSB. These actually work really well. They're actually very efficient in terms of power used, and they're efficient in terms of bandwidth, and the message tends to get through. So they work really well, and it's taken a while to displace them with digital techniques. There is a lot of interest in digital techniques. The problem is that the evolving methods are relying on nasty proprietary speech codecs, which is something that I'd like to change. There's some advantages to getting the bit rate down quite a lot for digital radio channels. If you can compress it more, you can make more use of you can allocate more power to each bit and have a better chance of getting that message through. So through that noisy channel that's prone to bit errors. Other advantages are you use less transmitter power and you save on battery. So I've got a little slide here that tries to indicate the advantage of a lower compression rate, a lower bit rate over the channel, or better compression. On the left there we have, imagine you've got 1 watt to transmit over the channel, and this is your signal sticking up, and this is the noise floor. Now imagine a radio channel, it's a bit like this hall. Currently I'm talking fairly loudly, I've got amplification, you guys are pretty quiet, so my message is getting through quite well to you. But if everyone was making a lot of noise, the noise floor would rise, and I'd need to use more power to get my message through to you. Now, if this is the situation at 1400 bits per second, imagine we used a codec that wasn't quite as good, and it was, as on the right here, 28 bits per second. We now have to transmit twice as much data, and one way we could divide that is into 2 signals. Still a total of 1 watt going over the channel, but in this case 2 signals, we're not allocating as much power to each bit that we're sending over the channel. And that means we're down amongst the noise on the radio channel, so when we try to pick up those bits in the demodulator and the radio receiver, we've got a much better chance of getting an error, and we'll have some problems with picking up the signal and getting good quality speech. So the message here is that if you can get better compression, you get better power efficiency, you go further with each watt over the noisy digital radio channel. This is a bit of a mud map of a traditional, ooh, lost the lights, that's okay. Better? Okay. Good, okay. This is a basic digital radio system. We have a microphone that samples the input speech through an analog to digital converter. Now that'll give you a sequence of samples, say at 8,000 samples per second, 16-bit integers, which is the basic coding rate. That'll then get sent to some sort of codec, in this case Codec 2 for compression. We then do something called forward error correction, FEC encoding. What that does is takes the 1400 bits per second bit stream and adds a few extra bits. These bits are used to protect the payload data in the 1400 bits per second over the digital radio channel. So they're redundant, but they're added to protect the main payload data. We then pass that through a modulator, which gets the digital data into a format suitable for going over the radio channel. We send it over HF or VHF radio. The demodulator takes that data off the channel and gives you a bit stream, which we feed to the forward error correction decoder, the FEC decoder down the bottom here. Now that looks at the data that's received and uses some of the redundant information to correct any bit errors, which are then fed to the Codec 2. So we'll have a 1400 bits per second stream here that's fed to the decoder, which will then generate a 8,000 bits samples per second signal that's fed to a digital analog converter, which we then can listen to. So that's the context.
Process gain from the FEC?
I beg your pardon?
Process gain. Do we get it from the FEC?
It's possible depending on the codes and the modulation method that's employed. One thing to realise is that voice is not like data. The way most data networks work is if you get a single bit error in the entire data packet, the CRC fails and we reject the packet, and we might ask for another one or we might discard it and move on. Voice is not like that. If you get a few errors, 1, 2, 3, even 10% bit errors, it's likely you can still decode that packet and still get some useful voice quality out of it. So you've got to treat voice systems differently to you treat data systems to get the maximum potential out of it. You can even discard or lose an entire voice packet. So often the codec information comes along in packets. It might be 7-byte packets, 56 bits. If you lose one in the middle due to a burst error over your channel, you can often synthesize or estimate what was in that missing packet because there's a fair bit of correlation in speech between adjacent frames. So bit errors, random bit errors, or losing the packet, there's still a lot of very usable information there. You don't want to discard it. Unlike a data signal, where usually if the data's not perfect, you don't want it. And the reason is that the consumer of the speech is our ears, and they're fairly robust. If we hear a click or a pop, chances are we can still understand what's being said. It's not like you're putting an image on a screen or some text that'll be meaningless if it's garbled. The other thing to know about digital compressed data is that some bits are more important than others. So there may be some bits that are in error in the speech packet that you won't really notice the difference. Others that'll make it annoying, even painful to listen to. If you get an error in a bit that carries the energy of the speech for that frame, it might squeal or make a nasty sound in your ear. Some other bits you may not even notice if it's a bit that handles, say, a little bit of the high frequency data. So not all bits are created equal. Now you can take into account all these factors to design a better system. For instance, you can use unequal error protection of the data, or you can choose not to protect all bits to get a lower overall bit rate over the channel. Or you can even map the way you design your modulator and demodulator to get an optimum system, an end-to-end implementation that's designed to take voice from one side of the planet to the other with the minimum amount of bits. Okay, look at this guy. This is something I found on Wikipedia. It's a ham radio operator from 1924, and he's basically doing wireless communications with the technology of the day. And what I'd like to do is draw some parallels with what the ham radio guys were doing and what we were doing, because I put it to you that if this was 1924, we'd be playing with stuff like that. It's the same sort of geek sort of ethos of sharing, developing, and just trying things that are a little bit crazy, like a vacuum tube radio on skis somewhere in Germany in the 1920s. This was back in the time where people didn't know how to build the best radio. There were various different radio architectures drifting around. Tuned radio receivers, super hets I think had just been invented. I'm not sure if FM had been invented yet. It was probably AM or Morse code they were playing with. So these guys didn't exactly know the best way to build radio communications, but they were in there experimenting, and they basically influenced a lot of the radio systems that we use today. So very similar to the sort of stuff we do, 100 years later on. So you see these guys as the proto-geeks. They were experimenting with radio about 100 years ago. Very early on, they weren't even using electronics. They were using mechanical techniques to generate radio signals, spark gap transmitters, magnetic filings that used to be used to detect the signal through sort of magnetic effects. But then around 100 years ago, vacuum tubes got developed. You could suddenly start amplifying the signals, and electronics was born. And it was a lot of these guys were amateurs. They were just geeks of the day who liked experimenting in basements with strange things for the fun of it, sharing ideas. The birth of electronics led to computers during World War II with thousands of vacuum tubes, and basically before computers were around, ham radio was what you did if you were into a geeky hobby, ham radio and electronics. And what they were doing, they were building technology, they were communicating with other people doing the same thing. They experimented, they even did things like open hardware. One guy designed a radio, he published the design in a magazine or something. Another guy had modified it, and the same design would trickle through 10, 20 years of development, people sharing. So very similar to what we do today in the Linux community. So ham radio is still around, very vibrant, lots of people experimenting with it, doing lots of cool things. It's an experimental service, and one of the keys to the hobby is the need to be able to experiment, understand and modify. It is evolving from analog to digital communications. At the moment there's a lot of work going on with digital text type modes, but digital speech is still lagging a little bit behind. And one of the issues is that we need a non-proprietary codec. I'm the author of Codec 2, the primary author. I was first licensed as a ham radio operator at age 13, and I got my first computer a year later. So I feel kind of privileged that I grew up in this era where computers were just coming up and leading to where we are today, and ham radio was still around at the same time. And I really got my start in ham radio, so I feel compelled to keep contributing to it, because it's led me in a really fun career and to doing things like talking to you guys today. A little after that, I got involved in speech compression. Towards the end of the 1980s, it became possible to actually build speech codecs that could run in real time. The technology was around for a while in theoretical form, but the problem was it took about 30 minutes of workstation time to compress 3 seconds of speech. It wasn't until we got the silicon around, early DSP chips, that we could actually put these things into real time. So that was a lot of fun, doing a lot of embedded assembler, trying to get things very optimal and playing with the DSP algorithms to get them to run fast enough. I now work in full-time on open software and open hardware, mainly for developing world communications, and lately on the codec. So I'd like to talk a little bit about proprietary codecs. The sort of codecs we're dealing with in this space are sub 5,000 kilobits per second. They come in hardware or licensed software form. In hardware there might be a DSP chip that's been ROM programmed or flash programmed with a proprietary algorithm, a speech codec running on a DSP. Or in licensed software form, it might be something you can license under some sort of licensing terms and might require keys and dongles and that sort of thing. It's difficult to distribute because it's proprietary. You can't just download it. You can't be modified. In fact, the license will say it's illegal to modify it under the license. And of course, understanding how it works is discouraged. And that's really against the open ethos of both ham radio and the sort of things that we believe in. There's a problem with codec royalties. About 10 years ago, I used to run a computer telephony business. We built PCI cards that you could plug telephone lines in to. Our customers wanted G729 and we got quoted $40,000 to license it. We couldn't afford it and that hurt our business. So as both a codec user and a codec designer, I have some problems with codec royalties. I mean, we can get a first-class operating system, several of them out there, for free, and yet we're forced, or people try to force us to pay royalties for a tiny bit of software on it, the audio or video codecs. I've found it to be a useless tax on business and communication. I've yet to see any evidence that any of the royalties that go back into codecs get used to improve the world at all. They just seem to really improve the world of the people who hold the patents and the licenses. So, the way I look at it is basically a closed source codec makes a small number of people very rich. An open source codec helps a large number of people. So, for me, it's a pretty easy choice where I want to work. I'd like to talk a little bit about codec patents. I've been involved in developing a couple of open source DSP algorithms, first an echo canceller and now the codec, and people always say, oh, patents, you can't get around the patents, things like that. So I've done a bit of thinking about that. Basically, the guys with proprietary and patent codecs borrowed a lot of the code from the public domain. What they did was took that code, did some clever things, added about 5% of their own work, made a really good codec, and then locked up that 5%. But the thing that bothers me is that 95% of that stuff was in the public domain in their codec. So it's almost like they've taken stuff that was ours, and now they're charging us for it, just because they added a little bit to it. So to me, it's like having toll booths on public roads, and they've just locked this up for us. So to build an equivalent codec, the key thing is we just need to come up with alternatives for that 5% that is patented. Most of the algorithms in these proprietary codecs we can use, no issue. They've been around the public domain. A lot of this is 1970s, 1980s technology, 95% of the algorithms. And we just need to work around the bits that have been patented. It does bring up some issues with bitstream operability, but if we can get it in early for services using our codecs, and then that won't be an issue. Okay, I'd like to talk a little bit about speech coding and what it is. The general idea is you take some speech samples that have got some sort of baseline coding applied to it, like for instance just being sampled, so 16-bit samples at 8 kilohertz. Then we want to compress it. The art of speech coding is what can we throw away? There is a lot of correlation in speech, the signal doesn't change much over time, so that means that we can just send the bits that do change, and hopefully we'll get a good compression ratio. The aim is to retain intelligible speech. You should be able to understand what the person is saying at the other end of the link, and it should also be natural sounding speech. A limited case of that is when the speech gets robotic and you can't tell who it is talking at the other end. It just sounds like a speech synthesizer or something like that. So intelligible speech and natural speech, both of those become challenges, in particular as the bit rate is lowered. For very low bit rates, we use model-based speech coding. So we come up with a model of human speech production, and then we send the model parameters, and we update these model parameters at a constant rate, like every 20 milliseconds. We send another set of model parameters. That's different from waveform coding, where we look at that speech waveform and send sample by sample. So we tend to use model-based speech compression for the very low bit rates. Because the model is particularly adapted to human speech, we then run into problems with non-speech signals. Generally, these very low bitrate codecs won't do music, and they can struggle with even background noises that are not speech. So an example of a model parameter is the pitch. So as I'm talking, my pitch is varying over a certain range as I articulate syllables and sentences. For the human voice, the pitch range is around about 50 to 500 hertz. 50 hertz would be a deep male voice. He'll have some range in the 50 to 100 hertz range, and a young child would be up in the 500 hertz region. It turns out that you can accurately represent pitch, so you can reconstruct it at the other end of the channel with around 7 bits that are updated every 20 milliseconds. So that gives us, when you divide the 7 bits and update it every 20 milliseconds, you can represent pitch at about, the pitch of the human voice at about 350 bits per second. So that's an example of a model parameter being used to represent part of the speech signal. You then add to that a bunch of other model parameters, and you've got yourself a speech codec. The model I use is called sinusoidal speech coding, and I've got a few slides that illustrate that now in a graphical way, no maths, or very little. This is a graph of speech in the time domain. So along the bottom axis is time in samples, and that's about 320 samples, 40 milliseconds of speech. That's a female speaker, and it's just a tiny little fraction of a syllable that she's articulating. Okay, so one thing we notice about this speech signal is it's repetitive. As we trace along here, you see that this bit starting here looks a lot like this bit starting here. Maybe it's ramping up in amplitude, but it tends to repeat itself. When a signal repeats itself, we say it's periodic, repeats itself over a certain period. When it comes to speech, we call that period the pitch period. So that's just the pitch of this person talking. In this case, it's around, if we measure between these two peaks, it's around 35 samples. That works out to 4 milliseconds a period. So in time, there's 4 milliseconds. The signal repeats itself every 4 milliseconds. And that, if you work that out in hertz, that gives you a pitch frequency of 230 hertz at this instant in time. The pitch changes over time as the person talks. But if we just freeze it for this 40 milliseconds, that person's got a pitch of 230 hertz. Okay, now the fact that the speech is periodic does tend to repeat itself and only evolve fairly slowly over this, say, 40 millisecond period. That means if we can capture just a fraction of this and then reproduce it over the whole frame, we've got an efficient way to compress the speech. Now, this is the same signal, but we've plotted it in the frequency domain. So down the bottom, instead of time, we've got frequency. 500 hertz, 1000 hertz, up to 4000 hertz. The exact same signal, just looking at it on a frequency axis. Once again, we've got amplitude, or the height of the signal. Now, what we can see here is these spikes, or a comb-like structure. Turns out that because the signal's periodic in time, it's also periodic in frequency. So we get these spikes repeating themselves across the frequency domain, and they're known as harmonics of the speech. And the first one is at 230 hertz, the second one is at 460 hertz, etc. So they're just multiples of that pitch. So we have this duality between going back to the time domain slide and the frequency domain. So the way sinusoidal speech coding works is it says that, okay, they look a lot like a bunch of sine waves in the frequency domain. A sine wave has a single frequency, so that'd be a sine wave at 230 hertz, and that's another sine wave at 460 hertz, etc. So the idea of sinusoidal speech coding is we look at that and we say, well, okay, maybe we can represent this speech as a bunch of sine wave oscillators. Something like this. So we take one oscillator with a given amplitude, phase and frequency, another one, etc., and we just sum them together to produce the synthesized speech. So I'll illustrate that on the next few slides. On the top, we have 320 samples, or 40 milliseconds of input speech. This is from a male speaker. So you can see this is the start of one pitch period. Then we move along and this is the start of another one. And this is just the start of another one. Because he's a male, the pitch is a bit lower and it takes a bit longer to repeat itself. In this case, around 100 samples. And this guy's got a pitch at the moment of around 80 hertz, as distinct from the female. Down the bottom is we have the same signal modelled with a bunch of sine wave oscillators, but in this case we're just using one sine wave, so as a starting point. And what I'm going to do now is I'll have successive slides where we build up more and more sine waves, and the idea is we try and reproduce this original speech signal at the top. So that's with 3. You can start to see some of the pitch structure evolve now. The signal's repetitive. From this point here, it sort of goes down a bit and then starts up again here. So we're starting to get this pitch structure, but it doesn't look much like the original. That's with 10 harmonics. Now we're starting to get somewhere at 25 harmonics. We're starting to see this same sort of double notch at the top and the waveform decaying and then starting up again. It is time shifted with respect to the original. by about 40 samples. You wouldn't be able to hear that, that's just a very small delay if we played that out of speaker. So there is a time shift, and by the time we get to 50 samples it looks really similar to the original. So that's just a quick graphical explanation of how you can synthesize or model a speech signal with a bank of sine waves. Okay, so 50 sine waves sounds like quite a lot of information we need to transmit, but it turns out that because all the frequencies are related, they're harmonics of each other, we really only need to send the frequency of the first one. So in that case we'd just send the frequency, basically the frequency of that sine wave there, 80 Hertz, and then the rest are multiples of that. Here's an example of the bit allocation of the alpha codec. We transmit one of these frames every 40 milliseconds. We use 32 bits every 40 milliseconds to transmit the amplitudes of all the harmonics. The frame energy is actually updated every 20 milliseconds at 5 bits a frame. There's some voicing. Voicing information conveys whether the speech is a vowel or a consonant. A vowel has that pitch structure that you saw. A consonant is more noise-like, and so we have a little flag that determines that, and that's updated every 10 milliseconds. And then there's the pitch information down the bottom. Okay, I've got some samples I'd like to play to you now. First of all, I'll play just the standard male sample that I use for a lot of the development and testing. You may find that the samples are reasonably close when I play them through these room acoustics. I'll be playing an original, a 1400 and a 2400 sample. The reason is the room basically modifies the signals so they all sound the same before they go in your ear. I encourage you to jump on the website and listen to the samples through some headphones, and you'll really hear the difference between the codecs. The speakers muddy things up. It's like looking at things through glasses that don't work right. Whereas when we use headphones, it's a bit like using a microscope to really pick what's wrong with the signal. So we tend to, because when we're developing it, we're looking at for very small artifacts, we tend to use the headphones. And then once the thing's in use, it'll be used through a small speaker and a radio, and it won't matter so much. I'm also going to play some samples of a signal with background noise and show how that can affect speech codecs. Okay, so first this is the original.
The Navy attacked the big task force.
1400.
The Navy attacked the big task force.
2400.
The Navy attacked the big task force.
And this is through another codec.
The Navy attacked the big task force.
LPC10 is like a 30-year-old 2400 bits per second standard that is open, but it's sort of old school. So I'll do them again.
The Navy attacked the big task force. The Navy attacked the big task force. The Navy attacked the big task force.
That's awesome. Yeah.
The Navy attacked the big task force.
Yeah, no, they did. But like I said, try it through headphones. It's not quite so awesome there.
Can you show that in detail, please, so we can see the size of those files?
Okay, sure. Perhaps alright then I'll do that. View.
Show that much because they're uncompressed.
Oh yeah, this is after they've just gone back to linear wave files for the purpose of playing. So. Good idea though. Yep. Now I'd like to play a sample with background truck noise, and I'll play it at 2400, the original 2400, and then using one of these older codecs that can't handle background noise so well.
It's easy to tell the depth of a well. It's easy to tell the depth of a well. It's easy to tell the depth of a well.
So what's happened with that last codec is that the background noise has actually messed with the speech coding algorithm. The speech codec has broken down, whereas I've done a lot of work with that sample, so I've made sure it plays really well. But even so, you can hear it does still mess with the codec a bit. The truck noise was designed to mess with speech codecs as it's periodic as well, so now and again the codec gets confused that it's human pitch.
So that's what those telemarketers use when they ring you up.
Okay. So, developing speech codecs, they're really complex DSP algorithms. I did this stuff for a PhD, and then I'm building on top of that PhD work for this stuff, and it hurts my head. I'm getting too old for this sort of stuff. But you've got to work out how to debug them, just like any other piece of software. So what we tend to do is run the codecs in non-real time. I take those sort of stored files, I play them for the codec, output another stored file, listen to it. And what I also do with this codec is I dump values from the codec every frame into a bunch of text files, and then I've got some GNU octave scripts that let me plot the internal waveforms. It's not much good me looking at a list of numbers. I need to visualise this complex data some way so I can debug these these DSP algorithms. And I've got a way in Octave to single step through each frame, so I can step through frames back and forth and watch the codec doing its thing, or screwing up in some cases. So this is a typical sort of plot that I'd have. This is the input signal up here. That's part of that Navy attack, the big task force you heard before. This is the spectrum of it over here, so in the frequency domain. And then this is part of the pitch estimator that estimates the pitch of the human voice as it goes through. So these waveforms here are various steps of processing the waveform. And then finally we get this output here that's got a peak around 100 Hertz, which just happens to be the peak, the pitch period of that frame. So this is the system I use to debug the pitch estimator, and down the bottom in the console that you can't read very well, is a little just forward back button to track through the algorithm and see what's going on. Then when I work out what's going wrong, I go back to the C code, play around with it a bit more. And lots of listening as well, just listening to that same file again and again and again. And you go nuts, you listen to it, you think you found differences, you wake up in the morning, listen to the same files, and you can't hear the differences anymore. And, there we go. Codec 2 and weapons of mass destruction. I started releasing the 1400 bits per second codec a few months ago and said, hey, these things are banned in the US. They're under export control. You'd better check Australia because they tend to follow a lot of the same rules. Sure enough, I found a website, and Defence Export Control Office, DECO, has this big web file. So I'm reading it. Uranium, certain chemicals, nuclear weapons design software, speech codecs, beneath 2400 bits per second. Oh dear. So, yeah, well, I started scheming on ways to, do that sort of thing, but basically I gave the guys an email, and they said, fill in this form. And I tried to explain what it was all about. I mean, I'm not really exporting this. The form says, who are you sending it to? Yeah, and how much are you selling it for? And I'm sticking it on a website, but so I wasn't sure how it maps to their model of export control. But the form actually said weapons of mass destruction at the top. That you can download the PDF, so it's got. Yeah, is it on the list, or is it on a list of banned, precursor chemicals for weapons of mass destruction? So I filled it in, a form with WMDs on it, and I got an email back saying, look, they've decided it's been assessed as not controlled, which means they don't care, and they're going to send me a fancy certificate. And there'll be a good blog post in that when it comes out. But I haven't got the certificate yet, so I can't publish the code. I'm just waiting. So that's the end of the talk, and open to questions now. Mr. Microphone.
I'm just wondering if you have enough noise in the digital transmission to break down the forward error correction, how much bit error rate can you tolerate beyond that before it really stuffs things up?
Yeah, we haven't really tested that on this codec, and if you'd like to try, that'd be very welcome. It's quite easy to do, just submit the bit stream, but typically 5 to 10% random bit error rates, which means you've got to design a modem that can hang on at 5 to 10% bit error rates. Not many modems do. They're all designed for very low bit error rates for traditional digital data. Yes?
This actually ties into Bruce's keynote this morning. Have you got any inclination on how hard this would be to implement in a FPGA or in hardware? Because this would be such an awesome idea in hardware. Yeah, well, basically the easy way is we'll probably get it down to something that can run in a big microcontroller or a small DSP eventually. And that's the easiest way to do it these days. They're only $2 or $3.
Yeah. Have you done much work with testing non-English voice coding?
Non-English? Yeah. I haven't, but I get people sending me samples from all over the place. Most human speech is pretty common, except for stuff like the Hottentots in Africa and things like that. So even tonal languages like Asian languages tend to go pretty well through these things.
Coping with background noise, is there a possibility of removing it rather than encoding it and still leaving enough bits left over for the speech?
Yeah, that's a really good idea, and that's what John Mark here has done some pretty good work with the speech software to remove that. He's going like this, but it is really good work. Yeah, and that's a great approach. Yep, you can actually make it sound better before you code it. Unless you're doing something like emergency services where they want to be able to hear the sirens in the background. There are some dangers with that approach, yeah.
You mentioned quite a lot about the modeling to try to create a model for speech so you can compress it more finely. It seems like a lot of the parameters you mentioned are then related from sample to sample. Do you then apply something like arithmetic coding or something to further compress?
Yes, because there's correlation between frame to frame, you can send differences or decorrelate that further.
Okay, but you do that in a second pass after doing the modeling?
Yes.
Okay,
yeah.
thanks.
The actual model runs at 10 millisecond rates, and then we do other things and eventually sending it at 40 millisecond frame rates.
With the amplitude spectrum, do you do anything to limit it to like the formant areas, or?
There's only sort of just basic band limiting at either end, 200 hertz to 3500 hertz. That is a bit of a problem in that you never know what sort of microphone people are going to use to send to you. So some samples I get have a lot of information down to DC. Yeah.
What sort of latency are you looking at through the entire chain?
Yeah, probably 100 milliseconds, same sort of thing as your GSM handset. No, latency.
Latency. Sorry.
Latency.
Yeah.
Yeah. Yeah, so in the order of 100 milliseconds end to end, similar to your mobile phone.
Okay, so still long enough that you're not going to be able to say sing in tune with another person, that sort of stuff.
With a lot of digital radio applications are push to talk, so even latencies you won't notice them because there's no receive signal coming back while you're talking.
Okay.
So it's a little bit of less stringent than say a two-way thing where you've got echo issues and two-way. Yeah.
And thinking of something like singing where you've got a pretty clear spectrum as opposed to speech, which gets all muddled up.
You wouldn't really use this for singing. You'd go and use Opus or something.
Well, what I'm thinking is, are you able to?
He's been doing just what you did.
Well, I was thinking also of the Celt codec, which is now called something else. Thank you. Yeah. Which is probably the next talk or something like that. But are you able to use, sort of recognise, okay, I've got enough bits in the frame now that I don't actually need to send any more? Can you?
It's not variable bit rate, so it basically just looks at what's there and sends it.
Okay.
Yeah.
No worries.
How will you respond when some company picks up your codec and does the 5% and turns it back out?
I don't know. I write them a letter.
So, David, John Ackerman and I have talked about that, and one of the responses actually is to pile on. And the reason for that is that there just happen to be a lot of hams in the United States who are attorneys. And we have a really nice big pro bono, that means volunteer and free, law staff to help with this if it's necessary. So you get to things like invalidate the patent, bring suits. You don't have to wait to be sued. You can sue, and if we look at the JMRI case, there's a case where the open source developer actually sued the patent holder. And what happened was that when the patent holder actually got to court, he decided he could not defend his patent and he disclaimed it. So sometimes we win.
Yeah, one thing I would like to do is get a patent search done, so if anyone's interested in playing with that, look at everything we're doing and make sure it maps to non-existent patents, because now's the time to change anything if we do need to.
Last question. Have these things got enough grunt, the Leo sticks got enough grunt to do the encoding?
What sort of CPU
are they? In the conference. 16 meg.
Are they an AVR or a 32-bit?
Yeah.
Probably not an AVR, but it's 32-bit, big brother. Okay. People are using those little development boards to do it now, and that's in floating point.
Okay, so this sort of second part of that question is, you talking about the voice being from 50 hertz to 500 hertz.
The
so,
pitch. The pitch.
Sorry, the
of-
pitch, yeah.
Yeah. The harmonics extend out to 4 kilohertz.
The bit you really care about is below the 500 kilohertz. So do you discard above that, or are you specifically looking at the audio frequencies above that
500
to
hertz
find
maximum is the frequency of the first harmonic. Then there's multiple harmonics of that, so the whole spectrum extends out to 4 kilohertz. That the 50 to 500 is just the fundamental frequency or the pitch. Yeah. So.
Okay.
Probably worth getting a comment from John Mark.
Do you want to? Do you want to
one
take
more?
him?
Yeah.
Yeah. Okay.
Actually, I didn't have a question. I just wanted to make a comment that I actually listened to David's audio files with actual headphones, and what he did at 2.4 kilobits per second with Codec 2 is actually, in terms of quality, somewhere between 6 and 8 kilobits for speaks. So that is actually quite impressive what he did.
Thank you.
Thank you very much, David. And on behalf of Linux Australia, I'd like to present you this gift.
Thank you very much.
Thank you very much.